Hi everyone. In this video, we will discuss about column, design of column. Column is a vertical compression member which effective length is greater than 3 times of least lateral dimension. Column is a vertical compression member which effective length is greater than 3 times of least lateral dimensions. If its effective length is less than 3 times of least lateral dimension, then we may call it as a pedestal. I am repeating it again. If effective length is greater than 3 times of least lateral dimension, it is a column. If it is less than 3 times of least lateral dimensions, we may call it as a pedestal. Right? Suppose least lateral dimensions means either width or length, whichever is less, width or depth, whichever is less, that can be taken as least lateral dimension. Suppose here x is equal to 200 mm, let us assume, and y is equal to 400 mm. Y equals to 400 mm. In this case, least lateral dimension will be x, right? 3 times of least lateral dimension means 600 mm. If length is greater than 600 mm, we may call it as a vertical compression member, that is column. Right? There are different shapes of columns are available in practice. They are rectangular column, square column, rectangular column, and circular column. The columns are classified based on the type of reinforcement we are using and based on the type of loading and slenderness ratio. There are 3 classifications of columns. Under the classification of reinforcement, there are 3 types of columns: tied column, spiral column, composite column. Tied columns means all the main reinforcement are tied with a lateral reinforcement. Right? Tied column means when the main longitudinal bars are confined with a closely spaced lateral ties, then we may call it as a tied column. Spiral columns means the column which is having spiral reinforcement is known as spiral reinforcement column. Composite column means in this column we will use a steel section or pipe with and without main reinforcement. Okay, in this composite section we will use a steel section or a pipe with or without the main longitudinal reinforcement. Next, coming to the loading type, there are 2 types of columns: axially loaded column and eccentrically loaded column. Actually, in practice, we cannot get the columns which are subjected to pure axial load. The code IS 456 itself allows the minimum eccentricity. We will discuss about this in a coming lecture. See, if the column is subjected to only axial load, it means that the line of action of load is acting on the central axis, then we may call it as axially loaded. If the line of action of load is acting at an eccentricity from central axis, we may call it as a eccentrically loaded column. In eccentrically loaded column, along with axial force, there will be a bending moment. We need to design the column for bending moment and axial force. Next, coming to the slenderness ratio. Based on the slenderness ratio, columns were divided into 2 types. One is short column and long column. Slenderness ratio means the ratio of L effective by least lateral dimension. If this ratio of L effective by least lateral dimension is less than 12, we may call it as a short column. If the ratio of L effective by least lateral dimension is greater than 12, then we may call it as a long column or slender column. Next, coming to the effective length, table 28, page number 94 will explain about the effective length of various cases. Effective length means the distance between the point of contraflexure of a buckled column. Suppose this is a column, the buckling curve will be like this. This point is known as the point of contraflexure. Here is also point of contraflexure, means zero bending moment is zero, right? The distance between these two points of contraflexure is known as effective length. In IS 456 table 28, I should go to 94. See, this is the table 28 in page number 94. There are 7 different cases. We have effective length values for these 7 different cases. Coming to the case 1, in this case the column is completely restrained against rotation at both the ends. Column is completely restrained against the rotation at both the ends. Then the effective length is considered only 65%. 65% of the length is considered as the effective length. If only one end is restrained against the rotation, then 80% of the length is considered as effective. If both the ends are restrained against the rotation, then complete length is considered as effective. Likewise, the effective length values were given for total 7 cases. Right? Based from table 28, we can also observe that this effective length depends on the end conditions and unsupported length. Right? Unsupported length means, suppose this is a column. Here there is a lateral support at here, and we have another support somewhere here. The unsupported length between unsupported length means the distance between these two supports is known as unsupported length. This is the supported length. This is the supported length, means the distance between two ends. Unsupported length means support to support. Next, slenderness ratio. Actually, slenderness limit. See, the column is designed to resist the buckling. Column is to be designed to resist the buckling. It means that the section should be designed such that the column should not fail by buckling. It should fail due to the failure of material only. We need to design the column such that it should fail due to the failure of material only. It should not fail due to the buckling. Right? In order to resist the failure due to buckling, IS 456 clause 25.3 recommends 2 statements, and it limits the slenderness ratio. See, the unsupported length, distance between lateral connections, the unsupported length should be less than 60 times of least lateral dimension. And it's also stating that if one end is unsupported, this unsupported length should be less than 100 b square by d, where b is the breadth of the section, d is the depth of the section. Next, minimum eccentricity. class 25.4 of page number 42. Same, the slenderness limit is also in page number 42, right? In page number 42, class 25.4 explains about the minimum eccentricity. As I said earlier, in practice, no column is subjected to pure axial load. There will be some eccentricity due to imperfection of work. As per IS 456, the minimum eccentricity allowed is L by 500 plus B by 30, and it is subjected to 20 mm. See, next, load carrying capacity. Page number 71 of class, in page number 71 there is a class 39.3 which gives the formula for ultimate load carrying capacity of the short column. Okay, this is the formula for short column subjected to lateral ties: 0.4 FCK AC plus 0.67 FI ASC. FCK means characteristic compression strength of concrete, AC means area of the concrete, and FI is the characteristic compression strength of the steel, and ASC is the area of the steel. This formula can be used when the minimum eccentricity is less than 0.05 times of least lateral dimension. This is the formula for short column with lateral ties. If you are using helical reinforcement, then the strength should be increased by 1.05 times. This value should be multiplied by 1.05. And there is another statement in this class: volume of helical reinforcement, the ratio of volume of helical reinforcement and volume of core should be greater than 0.36 times of AG by AC minus 1 and multiplied by FCK by Fi, where Fi should be limited to 415 Newton per mm square. Means here we need to use this formula is applicable for Fe 415 steel only. Yeah, these formulas, the earlier formulas are about are for only short columns. Coming to the slender column or long column, there will be some bending due to the applied load. See, the two columns with the same end conditions are subjected to the load P. But in short column, the deflection is 0. But in long column, there is a deflection. Due to this deflection delta, there will be a bending. That bending is equal to load multiplied by the deflection. Due to this deflection, there will be a bending moment. Class 39.7 in page number 71 will give the additional bending moments caused by the deflection in x and y direction respectively. These are the formulas for additional bending moments caused by the deflection in long columns. These additional moments can be multiplied by the factor K, which is given in page number 72. Right. Coming to the design requirements, these design requirements are taken from page number 48, class 26.5.3. For longitudinal reinforcement, the area of the steel should be in between 0.8% of gross cross-sectional area and 6% of gross cross-sectional area. It means that area of the steel should be greater than 0.8% of gross cross-sectional area and should be less than 6% of gross cross-sectional area. This is the minimum, this is the maximum. And for rectangular or square column, at least we need to use 4 bars. For circular column, we should use 6 longitudinal bars. The dia of the bar should be 12 mm and more. Minimum dia of the bar is 12 mm. The spacing between the two bars should be less than 300 mm. This is about longitudinal reinforcement. And coming to the transverse reinforcement, as I said earlier, generally we use two types of reinforcement. One is lateral ties and another one is helical reinforcement. In both the cases, the dia should be greater than 1/4 times of the main longitudinal reinforcement dia, or it should be greater than 6 mm. At least we need to use 6 mm dia as the lateral ties or helical reinforcement. This condition remains same for both lateral ties and helical reinforcement. And coming to the pitch should be less than least lateral dimension or 16 times of a small longitudinal reinforcement bar or 300 mm, whichever is less. The pitch should not be greater than these values. Okay, pitch should be less than least lateral dimension, 16 times of the dia of the bar, 300 mm. And in the case of helical reinforcement, pitch should be less than 75 mm or 1/6 times of the core, or pitch should be greater than 25 mm or 3 times of dia of the bar. In simple, we can say pitch should be in between 25 mm to 75 mm. Right? Thank you.